let's try and see a very simple situation and start reasoning it out from like the very basics. Okay, so imagine this is a person standing on the surface of the earth and say they're standing perfectly still. Okay, so what are the forces that's going to be acting on this person? Okay, so there's of course going to be gravity, this gravity that's going to be pulling them downwards, and it's going to be a constant value all the time, right? But we make this observation that since the person is standing still, they are not accelerating. What does that mean? Well, according to Newton's first law, we know that the net force on this person has to be zero, right? Because according to Newton's first law, if there is a force, then there must be a change in the state of motion of the object. Here, well, there is no acceleration, which means that the net force is zero. Well, what does that mean? Because we clearly see there is a force. Well, that means that there must be something that exactly balances out the effect of gravity. There's some mysterious force from somewhere that's like perfectly holding you stable, holding you steady on the surface of the earth, that's perfectly balancing out gravity somehow. And that's what allows you to, like, stand happily there. And what is this force? Well, if you think about it a little bit, the answer is maybe a bit obvious. So let me put it this way. So I'm sitting here on this chair. There is the force of gravity that's pulling me down constantly, right? But what is it that prevents me from basically accelerating downwards and essentially falling through the earth, right? Like why doesn't that happen? And if you think about it that way, then it's a bit obvious that well, it's the floor that's holding me up, right? There's something about the ground that is making sure I don't fall through it. It's the atoms of the ground are like they're jam packed, and they're like they provide an integrity that hold me up. Well, that means in physical terms, that means that the ground is applying an upward force, and that is what is holding me steady and making sure I don't fall through the earth. Well, if you take this inference to its logical conclusion, that means that whatever force this is, let's just give it a name. Let's call it normal force, okay? Because that's what the textbooks call it. So if this normal force is holding me up and I am not accelerating, well, that means that the normal force must be exactly equal to gravity. And well, this is something that we can infer purely based on the math so far, right? Now, let me ask you a question here at this point, okay? Because this is the thing that confused me quite a bit all the time. And the question is, are the normal force and the gravitational force an action-reaction pair? Okay. And what do I mean by an action-reaction pair? Well, action-reaction pair is the two forces that Newton's third law talks about. They're sometimes called as the action force and the reaction force. Well, call it what you want, but uh, is is it these two forces that the third law is talking about? Okay, and if you want, you can maybe pause the video a little bit and stare at the statement and think about this. And the idea is that it's very tempting to think about these two forces as the action-reaction pair because, well, they are opposite in direction and they are equal in magnitude, right? And the third law talks about something about forces that are equal in magnitude and opposite in direction. But the truth is, these are not an action-reaction pair, and that kind of becomes a bit clear. And if you take a look at the wording, if you really take a careful look at the wording of the third law, it talks about two objects, right? It, there's force F on object B, and then there's the reaction force, which is on a different objects. So not only does the third law talk about two forces, it talks fundamentally about two objects. Whereas if you take a look at what we've drawn here, we've drawn two forces on a single object. That is not what the third law is telling us about, right? So in this, if we want to apply the third law to this situation, we need to really take a careful look at what the two objects here would be. There's an object A and an object B, which are applying forces on each other, right? So this person here is experiencing two forces, but where is this force coming from? Well, that's coming from a different object, and that object, it turns out, is the Earth, right? The Earth is what is providing the force of gravity, and the Earth is also what's providing the normal force. So in each case, in case of each of these forces, we need to take a look at how the Earth also experiences forces. If we are to believe Newton's third law, which says that the two objects must apply forces on each other, right? So let's take a look at what this looks like. So here's my wildly disproportionate cartoon of the person standing on the earth. And let's continue our assumption that the person is standing perfectly still. Okay, so there is definitely going to be the force of gravity, which is pulling the person down. Okay, so gravity is causing the person to accelerate, causing the person to experience a downward force, and that is applied by the earth on the person. In turn, the earth will experience a force due to the person being in contact with it. Okay, so this is not something that's obvious from our previous discussion, and to really understand why this force comes about, we need to maybe take an analogy. So let's take an analogy here of say two friends where one is playing a prank on the other. Let's call this friend as the earth, and let's say this is you, and the prank is that the earth has tied a lasso or something around you and is pulling you towards itself. So you experience a force that that towards the earth, which causes you to accelerate towards the earth, basically, right? So you lose your balance and you respond to this force by accelerating towards it, towards the earth, basically, right? Now, if you if you keep accelerating towards the earth, at some point you are going to come very close to it. You're going to come close enough to make contact with the earth. Okay, and what's going to happen then? Well, if you think about it, once you come close enough to make contact, and once you do make contact, you're going to bump into the earth, and that is what is going to cause the earth to go tumbling. The earth is going to go tumbling backwards if it pulls too hard. You're going to just go bump into the person, and they just fall backwards, or they at least experience a force backwards, right? And that's essentially what's happening here. The earth is pulling you, but once you're close enough to the earth to make contact with it, the earth will experience a force that you apply on it by virtue of your contact. And the only big difference between this picture and this picture is that the earth's actual mass is quite big. So which is why the earth doesn't that easily go tumbling, basically. um, yeah, that's there. And now, according to Newton's third law, there is going to be a reaction force that you experience, that the earth applies on you. So this is the reaction force. Okay, this is an action reaction pair here, right? So this force and this force are an action reaction pair, and this is what we call as the normal reaction, okay, which we wrote as F normal. And the idea is that the normal reaction, being a reaction force to the force you apply on the earth, is not really its magnitude can actually change from the force of gravity. Well, what does that mean? So let's take a look at the previous argument we made. Okay, we took a look at just these two forces and we said they were equal and opposite, but that only applies when the person is perfectly at rest. Okay, if the person is moving or if they are jumping, that means that this object has to experience a net upwards acceleration for it to jump, right? If the person is jumping, they must experience a net upward force, which means that what they're doing essentially is they are applying a larger force on the ground. They're applying a larger force on the ground. Let me just use a different color because you can barely see that one. Uh, so they're applying a larger force on the ground, on the earth, and that causes the reaction force to be larger. And this is what causes an upward acceleration when you jump, right? So this is something that I think that people often get wrong when we think about all of this. So and finally, we have this one force that seems to just be like hanging and unpaired, which is completely wrong from a third law perspective. The answer to that is that it isn't unpaired. There is a paired force for it, and that's simply the force that you apply on the Earth. Uh, the gravitational force that you apply on the Earth, which has the exact same magnitude as the gravitational force that the Earth applies on you.